Welcome back to the Physics Society podcast series, PhysPod. We know it's been a while, but rest assured, we will be more consistent soon. Today's guest is Professor Geraint Lewis. Geraint is a theoretical physicist best known for his work on dark energy, astronomy, and cosmology, along with involvements in various other research projects. Geraint is not only an esteemed academic, being awarded with the Walter Boas and David Allen Prizes to name a few, but he's also a delight to have a conversation with about the mysteries of our universe. Besides his research, Geraint is also passionate about science outreach and communication, and is highly involved in that regard. This certainly includes 3 of his published non-fiction books, Where Did the Universe Come From? And Other Cosmic Questions, The Cosmic Revolutionary's Handbook, and A Fortunate Universe, Life in a Finely Tuned Cosmos, which we highly recommend you get your hands on. We talked about various topics from Geraint's research and explanations regarding some of his research, up to what it means to be a good physicist and how to get there. Hope you enjoyed this as much as we did, and here is our conversation with Geraint Lewis. Hi Geraint, thanks for meeting us today.
Pleasure.
No worries. So let's know a bit about yourself. Tell us about your childhood in physics and your fascination for science, and as much as you want to tell us about that.
Oh, childhood, that was a long time ago. So I was born a long way away from here, right? So I was born in Old South Wales, so the original, back in the United Kingdom. And I come from a sort of a country community, but it's country and industrial. So coal mining was the main industry, so there were coal mines around, but everything else was farmland. So I grew up not in a big city, but in countryside, but with industry, all the kind of stuff around. And with no scientists. So I didn't know any scientists at all when I was growing up, kind of thing. The only scientists I ever saw were on TV, and they were science fiction scientists, right? So Doctor Who and Quasars, if you know those kind of guys. So I didn't really have much of an idea of what science was. I like most kids, I had books about. There was a series in Britain called How, Where, What, and Why, which was just like all kinds of topics, lots of colourful pictures describing kind of stuff. I never thought about being a scientist, and I was never an astronomer as a kid. Wales is famous for having cloudy, rainy weather, so you can't see the sky anyway. So I at some level, I sort of stumbled into becoming a physicist. I didn't know what I wanted to do when I was growing up. I figured I would just go into industry like everybody else around me. I wasn't super strong at school until I got to about 16, and things clicked. I suddenly discovered I could do maths, and I suddenly discovered I could understand physics. And I hadn't thought about going to university. One of my teachers suggested I should think about going to university. I thought, what am I going to do? Should I do something useful like business, or should I just continue doing physics and maths? And yeah, so I just sort of trundled along this path. I went to the University of London first, did a degree in physics and astronomy, thinking that I would then go off and go into business. But I did well, and somebody suggested I do a PhD, so I applied and I got into Cambridge and did my PhD at Cambridge, and it's just sort of continued that way. So I never had this strategic plan of being a professor when I was a kid. If I wanted to be anything, I wanted to be Doctor Who. But yeah, I basically have, by luck, ended up in this particular situation. I'm not sure if that's meant to be an inspiring story or not, but...
I have one question though.
Yeah.
Which Doctor Who is it?
Oh, well, see, I'm a child of the 70s, and so it was Tom Baker was my Doctor Who. That's when,
Fair enough.
yeah, and he was the best, of course. But
I remember we had I was on the Slack for Sci-Fi, and he had I think you still have the robot logo, the Martians, or the Moonlanders, or if that's what they're called. I don't know correctly.
I'm not sure which one do you mean?
It was your logo.
Oh, the Cybermen, yes, of course. Yes, they are. They're my favourite Doctor Who villain as well, yes. I was just trying to work out which villain you were talking about there, yes. Yeah.
Okay, this is my question. Who do you think has influenced you the most in your scientific career, whether that be like family member or Doctor Who or on TV?
Oh, I find these questions kind of hard to answer. The influence I got was more from reading than from people.
Yeah.
I definitely had those teachers that pointed me in the right direction. Yeah. My physics teacher at high school was definitely very supportive, and again in Britain, equivalent of the HSC is called the A levels. I had a physics lecturer there. Again, was very, very supportive. Yeah. But I got into reading books and books about physics, and so there's an author, Paul Davis. Do you know Paul Davis? He was based in Australia for quite a while, but he's now in Arizona. He in the 1970s started producing books on the nature of time and eventually on superstrings, all that kind of stuff. So reading lots of those books were inspiring in the sense that I realized that physics was about mysteries, right, and solving mysteries, and that it wasn't done, it wasn't complete, and there were still lots of things to solve. So yeah, I can't really pinpoint a person or an individual. I knew the story of Einstein from a young age though, because I share his birthday. Yeah, so yeah, 14th of March. I was born 90 years after him. So I knew that from an early age, but I never really understood who Einstein was, of course, until you get into high school and then to your university degree. So I knew about these people, but yeah, said the inspiration, I can't think of a single person, but there were lots of people along the way. Said that kind of steering really helped.
That's great. That's a good thing into a question I had, which is, what's one scientific mystery that you'd love to see solved in your lifetime? Like, if you had to pick just one to just see, like...
Oh, does it have to be one?
Just one.
Oh. The one big scientific mystery I really would like to know is our universe alone, right? So, and that's tied to lots of other questions about the universe. But to me, you know, the mystery of what kicked off our universe, right? What put the spark in the Big Bang, or however you want to put it, was that a one-off event, or was it something that produced this thing called the multiverse, right? Are we just one of many universes? And some people grumble a bit when we talk about the multiverse. They sort of go, oh, you know, that's not science, and we'll never be able to test it. But we don't know. We don't know yet because we don't have robust scientific theories of how a multiverse would work. So we don't know how testable it is. So I have my hopes up that it could be something that's tested in my lifetime. But, you know how physics goes, right? Sometimes things are sorted quickly, other times it'll take centuries. And so we're not guaranteed to have our wishes answered, right?
Yeah, that's great.
So you mentioned books,
Mm-hmm.
and you have written 3 books, if I'm not
Yes.
wrong. Tell us about that. How's the experience of writing a book? How do you feel about your books? And tell us a bit about the book's journal.
Oh, okay. So I can tell you how it started. So you know Dr. Carl is in this building. I've known Dr. Carl now for like more than 2 decades, right, since being here. And I was chatting with him back early 2010s, right? And we were talking about various bits and pieces, and his assistant there was Caroline Pegram, and Carl, of course, writes multiple books per year, and I sort of said, I wish I could write a book. And she said, well, why don't you? And I went, yeah, why don't I? And so I decided, because I've got scientific papers, and they're very important, but writing a book is something different to writing a scientific paper. You're trying to get a different message across to a different audience. So I decided that I would go down that path, and the question was, what would I write about? And of course, there's already lots of books on cosmology, there's books on mysteries of physics, etc. And I tried to think of a topic that hadn't been somewhat done to death by all of the other authors out there. So the first book I actually wrote with Luke Barnes, who is now at the Western Sydney University. He was my honours student here, a master's student, and then he went to Cambridge, did his PhD, etc. And we decided to write on this topic of fine-tuning, right? So there's the cosmological fine-tuning, they call it, right? Why is our universe almost seemingly set up for us to be here? And some people think, oh, that's a frivolous question, that, you know, clearly we are a reflection of the universe, right? I mean, it's not like we are beings from outside the universe and being dropped in. Our entire existence is tied to the properties of this universe. But if the laws of physics had been subtly different, right? Gravity had a different strength, or electromagnetism was different, etc. You can easily destroy the universe, okay? So we exist because we're beings of complexity, right? We're built of the 92 natural elements into all this array of molecules in your body, and it's easy to rub all of that out, right? By just messing around with the fundamental forces. This had been written about in books, etc., but it was always from one side or another. So there is the physics side and there's the theological side. And there are people that use this as an argument for a supreme being, etc. So Luke is a theist, I'm an atheist. Luke and I decided that we would write the book about the science of fine-tuning, right? So that's the vast majority of the book. And then in the final chapter, we would do a little bit of pop psychology, where we would play off our arguments against each other. And we said, we'd set out to write 80,000 words and ended up with 120,000, etc. And yeah, it was very satisfying to see the book published. And it's not like it used to be in the old days with science books that they sell millions of copies. So if you sell tens of thousands, then it's really good. So we're very happy with that. And then after that, it's just like, what do we do now, right? We've written one book, we're on a bit of a roll. What else do we want to write about? So the second book, I also wrote that with Luke, which is the Cosmic Revolutionaries Handbook. And we wrote that book because we get the same thing every time we give a talk on cosmology and about the universe. There's always a retired male engineer who comes up and says, you guys don't know what you're doing, that isn't the way the universe works. I have an idea about the way the universe works, but scientists won't listen to me. So the way we wrote that book is a bit of a self-help guide in the sense that if you want to overturn the Big Bang, modern cosmology, or any scientific theory, there are a set of bars that you have to pass, right? So we all hear about the scientific method and explaining data, etc. And of course, many of these people haven't encountered that really, right? This is the way science progresses. So we wrote that book with that kind of guide, but of course, really it's a book on cosmology about how we understand the universe and why cosmologists, and dangerous word, have faith in our cosmological model. Right? So that again, that book came out at the start of COVID. We were planning a book tour in the UK, just border shut, etc. So we haven't had a chance to go around and talk about that one. We did go and talk in the UK on the Fortunate Universe book, the first one on fine-tuning, and that was really good audiences, lots of questions and things, so that was very exciting. And then the third book I wrote with Chris Ferry, who's down at UTS, and Chris is well known for he's got a series of books for babies, so he has quantum physics for babies, cryptography for babies, and all this kind of stuff. But he wanted to write a book with a bit more substance to it. So the third book is about how in modern physics, gravity and the other forces just don't fit together, right? So you've got relativity and quantum, and they just butt heads, but we need both of them to explain the universe. So it was, again, a layman's guide to just how do we go around dealing with the fact that we need these two things, but we know that it's not the complete picture. Another book that came out during COVID, I've given lots of talks online about it, kind of thing, but again, it would be good to get out in front of audiences and probably talk about those books.
What are some challenges you experience writing it? Because writing, as you said, writing papers, one thing.
Yeah.
Talking to a completely different audience in a language that I kind of understand now, being in this position where you read more papers and you get more technical.
Yeah.
There is this whole idea that you kind of tend to close your eyes on the big picture sometimes and very get stuck into your problem that you're solving, and obviously talking to that different audience requires you to step out and look at that big picture. How was that?
Yeah, so I've always been interested in science outreach, so I've always done lots of talks to the public, and so like for many decades, several times a year, you've got to give a talk online, etc. So you get used to talking to your audience. The other thing which I decided for my own research career a while ago is that I didn't want to be pigeonholed. I didn't want to go down a path of just working on X. And so I would try to work on a broad spectrum of things. And so to do that, you've got to have a broad overview of what's going on. So, it is that being able to see the big picture, being able to understand what's going on in different areas and try and put it together as a coherent story and then sell it to somebody who's not an expert. It's one of those things that comes with practice, right? I mean, most scientists don't get training in talking to the public, and so you need to get out there and talk to your different audiences. But yeah, it takes time. That's the thing, and that is always the biggest thing that we lack as academics is time to do this kind of stuff. So I would love to write more books, etc. But there's only so many hours in a day, and we have to teach you guys, etc. So
honestly, that's one thing that I keep thinking was that I always want to do the outreach and I want to study as well, but I just don't know how you guys find the time to do the teaching and the research at the same time. It's
you just basically find all of your hours filled. That's what happens. Most academics don't really work the 37.5-hour week, right? They work above and beyond that. And part of that is because there's a passion there. Right? They wouldn't do it if they weren't interested in doing their research and selling the story to the public, all that kind of thing. So that it's that passion-driven thing. You know, I don't know any accountants, but maybe if I was in accountancy, I wouldn't feel the same passion for going out and explaining accountancy to the public. But you know, physics has that interesting aspect to it.
I actually remember, I think it was 2017 or 18, and I was in high school then, and I came to a lecture. I just saw it on Eventbrite or something like that. But there was a talk that you said on, I think it was the future of our universe. I think that was.
Oh yeah, the long-term future of our universe. Yeah.
And I came to that, and there was I've never been to UCIT before, and that's kind of like, there was a point that inspired me to say I actually want to do this, and I like the astrophysics part and physics part of it. And then I came, and I didn't know it was your talk, and then I came to, we were having lectures last year, and I remember I thought I'd seen you before somewhere, and that backtracked. I was like, okay, that's a cool, without knowing there was an inspiration.
Oh, it's not a very happy story, of course, about the long-term future, but it is the story that we can tell. So actually, recently, I don't know if you know, but the school does an OLE in Choose Your Own Apocalypse, where they get people to lecture on various ways that the Earth could be in trouble and get wiped out. And I do the astrophysical apocalypse. Mm-hmm. And again, not very happy stories, right? Big rocks falling from space, etc. But people are engrossed, right? It's a good topic.
So we could grab a bit of your wisdom and advice. What's your biggest piece of advice you could give to undergrad or postgrad students that want to emulate a career like yours, or
go
into
research? You don't want to emulate a career like mine.
Or go into research and.
I think the most important thing is to find what you love. And I know it sounds a trite thing to say, right? But if you don't find electromagnetism particularly stimulating, then going off to do research in that area, you're going to find yourself so it's find that topic that you love and find out, do I like doing the maths or do I like working in the laboratory? But it is that kind of, I really think that if you are going to be a success as a researcher, you have to wake up in the morning thinking, I got a question I want to answer, and it's a passion to answer it. That's the important thing. So, especially as undergrads, I think it's important that to take the opportunities to get research experience and go around and check out the different groups that you think might be of interest to you, just to see what they do on a day-to-day basis. One of the things is, of course, is that the public portrayal of science often skips a bit about how the science is done. Right? And so, if you go and look at the rooms where the PhD students are, they're all hunched over computers and they're writing code, etc. And you might not get that notion that this is the way research is done from your undergraduate degree, right? Because you're in there listening to lectures, etc. The way you get a taste is through the research various projects that can be done, and sampling the different areas. And I said it again, I think keep your eyes wide open. Don't be blinking. Don't come in on day one to university and say, I want to be a string theorist, right? It's like, what's going on in physics? What do I find interesting, and where do I think I can make a contribution?
Yeah, thank you. That's really good advice. Yeah.
But of course, everyone should do cosmology because that's the best.
Oh, of course.
Yes. So speaking of cosmology, you recently published a paper that had a bit of good noise in the public, with Brendan Brewer, on detection of cosmological time dilation of high redshift quasars. Could you tell us a bit about that and what was really awesome and significant about that?
Okay. So there's a couple of stories attached to this paper. So we know that we live in an expanding universe, and we describe that expansion in terms of Einstein's general theory of relativity. So we have equations that describe the expansion, and we ask what's the consequences of the expanding universe. And one of the things is that we should see the distant universe run in slow motion. So there's a time dilation. And the further back we look, the slower things should appear to go. So if you could see somebody like in a distant universe, they would be really running in slow motion kind of thing. Now, this was predicted a long time ago, 1920s, 1930s, people predicted that we should be able to detect this effect. But it wasn't until in the last decade or so, a little bit longer, that people have been looking at these exploding stars, supernova, and they basically realized that for a particular class of supernova, their explosions were almost identical, not completely, but almost identical. And so they would brighten and fade over a certain time period. And that they basically were able to show that when they looked out into, say, roughly half the age of the universe, they could see this slowing down the supernova. Okay, so the universe was behaving the way we expected, except it wasn't, because supernovae are not the only variable things in the universe. There are also these objects called quasars. These are supermassive black holes with masses billions of times the mass of the sun. They're surrounded by material that swirls around at speeds close to the speed of light. And that material, if you think about it, like you can imagine all this material tumbling around, there's all kinds of like almost weather, right? There's all kinds of things going off. So there's emissions in gamma rays and X-rays, etc. They're highly luminous. We can see them right across the universe, and they vary. They vary up and down. And people have been looking for this signature of time dilation in quasars, and they'd failed to find it. And so there was a guy working out of Edinburgh, Mike Hawkins. He had like 30 years worth of data that he had been able to get using the Schmidt telescope, which is in New South Wales. And he had light curves, and he was looking, and he basically said, something's not right. The nearby quasars appear to vary in exactly the same way as the distant quasars, which is not what we expect. And so, you know, that was a bit of a mystery, but those kind of mysteries, as you can imagine, guess, that they fire up the people on Quora and those kind of Reddit, and it's like cosmic mystery, cosmologist idiots, have they got cosmology wrong, are quasars out there in the universe, etc. So Mike published a paper in 2010 which really got the people on the fringe very excited. Now I think most cosmologists thought that the problem was that maybe there's not enough data and it's not of sufficient quality, and we don't really understand the variability of quasars, etc. So I had been looking into this for like a decade, trying to think about what the solution would be, but there just wasn't the data. But last year, there was a group in the US, and they published a sample that they have, 20 years worth of data on almost 200 quasars. And these objects had been identified in a big survey, the Sloan Digital Sky Survey. They've been monitored, so there were these intricate light curves. And in that period, we had statistically begun to understand how quasars vary, right? So they don't vary like a nice sine wave, because that would make life easier, but they vary more like the stock market, like sort of a damped random walk. But a damped random walk has got a time scale in there, a time scale of like returning to some sort of state. And so I said, oh, can I use that as a clock? Can I use that time scale as the tick for these quasars? So what we did is that I took that data and I was able to organize it so I was comparing like objects with like objects. This is one of the problems in astronomy, is often when you see two objects on the sky, they might appear very similar, but they are radically different things. So one could be a dwarf star, one could be a giant star, but much further away, but on the sky they look the same. So I was able to group things together, and I was able then to look for what signal was in there depending upon the distance, and out popped precisely the cosmological prediction about how things should slow down. And unlike the supernova, because quasars are so bright, we can see them over much greater distances. So we could see this slowing down back over 90% the age of the universe. And we actually could see the universe basically running a factor of 5 times slower back then compared to now. So yeah, that was very exciting. It was very satisfying to see. If we didn't see the signal, it would be like, oh, what's going on? Do we need more data? Because again, quasars don't have to care about our timescales, right? A decade to them, who cares? They might care about 100 years or 1,000 years or 100,000 years. That might be the timescale. But it looked like this damped random walk timescale set that tick for us, which was really, really good. So yeah, it was a nice little paper. I particularly like the analysis in there, so Brendan is again, he was a PhD student. He was my PhD student, but he is now a lecturer in statistics at the University of Auckland, and so he really thinks about how to work with data and how to extract all that knowledge. So yeah, it was a pretty cool result, and it sort of puts to bed the idea that quasars aren't cosmological, puts to bed the ideas that the universe isn't described by expanding space, so the universe is behaving the way we expect. As you mentioned, it generated a lot of press, but as always, timing is terrible, because I submitted this paper in January, and it takes a while for it to get refereed and all this kind of stuff accepted, and because it was in Nature Astronomy, you couldn't really have a news story until it's published, and so that didn't happen till I think it was June or July. And I happened to be at a conference in Europe. I was up in the Dolomite Mountains, and then I was at this conference to study something completely different. I started getting all these media requests about talking about quasars, etc. So it would have been nice if it was like the week before, the week after, but it just came during the week when everything else was happening. But it was good that there was attention from around the world.
Very cool. And what do you see the direction with this? So what's the next step?
Well, I think the next step is, firstly, we are moving into an epoch in astronomy where we're going to get lots more data very, very quickly, right? So there's already like the SKA being built in Western Australia, but there are other observatories being built, and their job is to basically understand the variable sky. So normally astronomers have looked at a patch of sky and may not go back and look at that patch for another 20 years. But it's realized that we should go back time and time again, because we don't understand the time scales that things are varying. So we will get samples of millions of quasars and their light curves. So we will tie that down and just make sure the universe really is behaving the way we want. Now, of course, as a scientist, you want to find things that don't behave, right? Because that just gives you new directions. But this is one of those fundamental properties of the universe that I think will hopefully hold out. But then the other aspect will be then, right, what does it tell us about quasars, right? We know they're supermassive black holes. We know their material swirling around really, really fast. But they're really difficult objects to study, right? I guess you haven't gotten into your higher year astrophysics courses yet, but believe me, gas swirling around, plasmas at relativistic speeds, very difficult things to understand. So it's unraveling that physics. So it'll be what's going on in those disks, what kind of outbursts are there, what's the magnetic field doing, etc. So I think for those people, this will be a real boon when they get all this extra data on how quasars vary.
Yeah, I was involved in astrophysics research last summer, and I never thought I'd hear the word turbulence this much, like gas inflow and accretion.
Yeah.
This involved and how difficult it is to simulate them.
Yeah. There's turbulence, which is it's one of those things that I know what turbulence is. Swishing water around. There's turbulence, but then you realise that we don't really. It's a difficult thing to, as you said, to simulate, even in water, to get turbulence right? Because of the way the water will act. But then add the fact that you want to make it a plasma moving at relativistic speeds in intense magnetic fields, and then it's a whole different ballpark. Which is why, with people like Don Melrose, and you look at plasma astrophysics, you go, it's complicated.
Yeah.
It's kind of a random question, I just thought of on the spot, but you talk about cosmology with so much passion. Are there any niche other passions that you have, completely apart from science, that you want to talk about or share?
Niche.
Anything really.
So you put on the spot.
Yeah. No. Okay, so I like history, and I like reading about history. So and I go through phases about the history that I read, and also listening to. I'm currently working my way through a podcast about the history of ancient Egypt. So I'm up to what is it, 1300 BC? So it's already been a couple of thousand years, but there's still another 1,000 years to go. So history is something that I've always been interested in. But I've got lots of little bits and pieces that I do. But I'm not skilled enough to say I make intricate models, that kind of thing. But it's reading and history, and a big movie fan as well.
Oh.
So especially classic movies. So and in fact, I'll do the same here. I was talking with my group meeting yesterday, so PhD students, etc., and we were talking about somebody had been to see the play On the Beach. Do you know the play? It's by an Australian author called Neville Shute. It's a post-nuclear war thing written back in the 1950s. And there's a movie made in 1959, and the people in there are all classic actors. There's Gregory Peck and Fred Astaire and Ava Gardner, etc. And none of the room had heard of any of them, and I was like, oh. So yeah, I'm a big fan of classic movies, going all the way back to like the 1910s onwards. So.
That's really cool. Thank you.
Yeah. Oh, and I also like science fiction. I should have also mentioned that, but I read a lot of science fiction as well.
Have you watched like Star Wars?
Oh yeah. Sorry, but I'm not a Star Trek fan, but I read a lot of science fiction. That's my train reading is normally science fiction and fiction books.
Oh, that's so cool.
Alright, I don't know if you've watched Oppenheimer, and one of the big themes is like, what is the role of a scientist? And I think personally, when I swapped into physics from doing architecture, I was thinking, oh, I've got a responsibility. I have to like do good for humanity or something like that. And I guess I was wondering, in what ways do you feel like you have a responsibility? What's your role as a scientist, and I guess the biggest scheme of things, learning about, I guess, the nature of the universe. Why do we do it in the first place, I guess?
So yeah, it's an interesting question, right? So the role of ethics and science, etc. Physicists, of course, normally dodge that question and sort of say, "Oh, my research has got nothing to do with making weapons and that kind of thing." Yeah. But clearly, just about any aspect of physics can be turned into a weapon. And so I think we just have to be we have to be careful, right? We do know that our mission is to uncover the way the universe works, right? That's what we are here to do. I don't want to use the word truth because we're getting to punch up to philosophers, but it's like, how does the universe work? Can I make predictions, etc. And we have to understand that along the way we will uncover things that, in the wrong hands, are going to be detrimental. The question is who do we decide makes those choices? Is it self-censorship? If I suddenly realize that I come up with a process where I can turn wood into nuclear material, do I just sort of say to myself, oh, that's it, I'm not going to talk about that, because it could be turned into a weapon, but that then also could be turned into a power source. So I think it goes above the individual, and it goes to humanity itself and how it wants to use what physicists find. I mean, again, watching Oppenheimer and nuclear weapons, I grew up in the 1980s in Britain. From an early age, I knew about the 3-minute warning, which is like, that's how long you've got from Russia launching missiles from Eastern Europe to them arriving. So I've known about nuclear weapons for a long time and their effect. And I think it's a choice for humanity rather than individuals to make about what we do with these things. Humanity could decide tomorrow that we don't need nuclear weapons. But of course, there are other issues, right? So that was a very non-committal answer, but I think it's a difficult question to actually answer. Again, if you ask yourself, could I put myself in the shoes of any of those people who were working at Los Alamos in the 1940s? And, there were young people there. Richard Feynman there, who was a young person. If he wasn't a physicist, he'd be a soldier or something. He'd be out from the Pacific. In that circumstance, you've got to think to yourself, would I want to work on this particular project? And I think until you're there and you know what the entire scenario is, I think it's a very difficult thing to do. Again, still very non-committal. Anyway, I would be happy in a world without nuclear weapons.
So this one is how we want to relate to whether it's in physics or whether just a passion that you have outward that you haven't explored yet. But if there's something you found interesting that you've never had the time to explore in depth, again, that can be a field in physics or an area of really niche something in physics that you always want to explore but never have done, or you will in the future? Tell us about that.
Not really in physics. One thing that I like to do, and again, I should have mentioned this maybe a moment ago, I'm a big fan of always trying to understand more maths. I don't think physics breakthroughs always come from understanding more physics. I think physics breakthroughs sometimes come from applying new tools to physics. And I think one of the problems that we have in physics is that we have our physics toolkit and we think that that's the only way to do things. And so, you do vector fields and things, and you think, this is it, this is the way the universe works. But you then look at the maths and you realize that there's more than one way of describing something. So my personal passion is, when I get time, is I try to understand more about the mathematics that I think I've missed, and also go back and looking at the history of physics to see where people have used maths and then it's fallen out of fashion. So Maxwell, when he was deriving his equation of electromagnetism, he used quaternions, right, which is these things that talk about rotations, etc. And that fell out of fashion because of the people who came after him. It was Heaviside and those guys who basically said, no, you should all use vector fields. And I'd say to myself, well, Maxwell wasn't an idiot. So what did he see was the advantage of looking at it from this perspective? And then you see that quaternions have evolved, through this Clifford algebra and there's geometric algebra, etc. And some physicists rave about these approaches to using this different maths. So I'd like to know a bit more of, the extensions of maths beyond the walls of physics. Never going to be able, of course, to absorb the entire library of mathematics because it's just far too much. But would like to see if I can find approaches from maths that can be applicable in physics that haven't yet been tried. That would be my goal.
I think we'll try to finish it up with a question from one of our PhysSoc members, and it's quite detailed in physics and cosmology. And the question is, if the universe is infinite in extent, then as you go back in time, how can an infinite universe shrink in size? How is it possible to start in a Big Bang at all?
That's because this student hasn't done my general relativity and cosmology course, right? So there's a misunderstanding. So there's a couple of things you have to be careful about. So yeah, if the universe is infinite in extent today, then with our standard theories, it's infinite in extent all the way back. Okay. So the picture that you have is that you have an infinite universe. You have material in the universe. Things are separated, and you take it back, and things get closer and closer and closer. So people talk about the singularity at the Big Bang, and because of various TV shows, everyone thinks the singularity means a point, but it's not. It's a divergence in our equations, and so we see that the density of the universe goes to infinity as we go back to the Big Bang. So it didn't start as a point and then become infinite. It was always infinite, even from that starting point. Yeah, I said the word point there, right? The other thing that you have to also be careful about distinguishing between the universe and the observable universe. So if the universe is infinite, we can only see a finite part of it, right? And that did start as a point and has been expanding ever since, but it's just a bubble in this infinity around us. So yeah, the answer is the universe, if it is infinite now, has always been infinite. So anytime past t equals 0, the universe is infinite. People don't like that answer, but tell you what makes them more upset than that is that when they learn in relativity that energy is not conserved, because they've had that beaten into them since high school, and said never asking the question of why it's conserved. So that's the first one to shake their boots a bit.
Well, thank you very much for joining us. I really enjoyed this. And
okay, I hope I answered your questions.
Thank you so much.
Okay.